forensic analysis of blood evidence. Introduction of materials. Good day. Today, we're conducting a forensic analysis of blood evidence. The following materials are essential in the crime scene. Always prioritizing the safety in the crime scene that involving blood evidence is a paramount due to potential biohazard. Treat all blood and bodily fluids as potentially infectious. Always wear appropriate PPE to prevent contamination of exposure to blood-borne pathogens. Personal protective equipment: gloves, face mask, laboratory gown, materials to be used, spray bottle, bond paper, used to analyze blood drop behavior on smooth surfaces. Evidence stands used to identify and analyze blood stains at a crime scene. Coloring or jubus. Protractor, used to measure the impact angle of blood stains. Cornstarch, magnifying glass, serves as a primary tool for micro-detail detection. Sponge. Dropper, droppers use release blood from various heights. Pushpin. Brush. Syringe allows analysis to release an exact blood. Cordon, used to prevent unauthorized ruler. Measure tape, used to ensure a dropper or a syringe is held at a precise height. Coffee. Yarn. Ketchup. Hot water. And cloth.
A forensic investigator analyzes blood evidence by first documenting the scene, then testing, interpreting the stains, and finally sending samples to the lab for confirmation. The goal is to find out whether the stain is blood, where it came from, and what it may reveal about the events at the scene. Blood evidence can help show where the injury happened, how the victim or suspect moved, and whether the scenes support witness statements and bloodstain patterns. Analyze. The investigator may also estimate the area of convergence and the possible area of the origin of the bloodshed. The blood drops of 3 feet that have fallen off 90 degrees freely onto a surface. They are perfect size and shape of a circle that have not have spines around. Non-voided series of drops show a continuous pattern of bloodstain without any interruption. This indicates that nothing obstructed the falling blood of it. An object was present, it remained in place. A voided series of drops indicates that an object or person was present and intercepted some of the falling blood, creating a gap or absence in the otherwise continuous patterns of drops. In that scenario, the blood may either the victim or suspect choose, because the falling of blood is not continuous. Removal of an object or individual after the bleeding occurred. Flow patterns are created when liquid's blood moves under the influence of gravity to pull down the blood to create flow. These are elongated patterns of blood that flow downwards on a vertical surface due to gravity. They can indicate the direction of flow and the position of the bleeding source relative to the surface. A large irregular shaped accumulation of blood at the center, indicating where blood collected or followed and settled on non-porous surfaces like in glass. Balls tend to retain their shape and have relative smooth smaller droplets radiating outward from the pool. The size and distribution suggest they were likely produced by an satellite rather than passive dripping along. The glass is smooth and impermeable, so the blood did not soak in. Instead, it formed distinct, well-defined stain with clear edges, and the pool appears somewhat cohesive due to surface tension. This combination of a central pole and surrounding spatter is common in scene where bleeding occurs with some force or movement, and due to the surface types, helps forensic analysis interpret how the blood was deposited. Unlike Douglas, the fabric observed the blood. The central pole is less defined and appears darker, thicker because the blood soaked into the cloth, spreading out and creating a blurred, feathered edge rather than a sharp boundary. The droplets are also affected by porosity. They tend to look less circular and more irregular, with feathering or wicking at the edges as blood seeps into the fibers. Some stains may appear elongated or faded compared to those on non-porous surfaces. The pattern shows a dense concentration of very small droplets, many appearing as a fine speck or mist with size generally less than 1 mm in diameter. Their appearance in the central area where blood impact, breaking up into numerous tiny droplets that radiate outward. The stains are tiny, often dot-like, are slightly elongated and spread over a relatively wide area compared to the size of the droplets. Some larger spots are present, but the dominant feature is the larger mess. It is produced by high energy forces such as gunshot wounds, explosion, or contact with fast-moving machinery. The blood is subjected to extreme pressure or speed, causing it to atomize into very small particles. This type of pattern strongly suggests that the blood was projected with significant force rather than falling under gravity alone or being cast off by swinging object. The spatter patterns appear to exhibit characteristics of medium velocity impact. You can observe distinct droplets that are larger than a fine mist but smaller than the large, heavy drops seen in passive driving. The central area show a concentrated parent, stain with radiating satellite. Spatter, which typically occurs when a forceful blow, such as a strike from a blowing object, hits a blood source. This is a low velocity because it produced by minimal force, such as blood dripping from a wound, a weapon, or from movement like walking. Gravity is the primary force acting on the blood. As you noted, droplets are typically 4 mm or larger. That means stain clearly exceed this size, confirming they were not profiled with high speed appearance because the blood is moving slowly. It forms larger, more cohesive droplets. When they hit the surface, they don't break apart into tiny pieces. Instead, they spread out or merge, creating the large pool in big spots seen here. Cast of pattern results when an object swung in an arc flings blood onto nearby surfaces. This occurs when an assailant swings the blood-stained object back before inflicting another blow. You can tell the direction of the impact object by the shape of the spatter. Counting the arcs can also show the minimum number of blows delivered. The pattern forms a distinct curved line of stains faced evenly and becoming smaller outward. Many are elongated with tails, and some vertical drifts are present. It follows an arc typically of a swinging object. Droplets are medium-sized, often tear-shaped, with tails pointing left, indicating movement direction. Medium velocity spatter caused by the momentum of a swinging object, enough force to fling blood but not atomize. While in the artery, because the blood is propelled out of the breached blood vessel by the pumping of the heart, and often forms an arcing pattern consisting of large individual stains with a new pattern created for each type. The heart pumps when a blood droplet hits a surface at an angle. It does not land perfectly round. It forms an elongated stain with a wider head and a thinner tail. The tail always points in the direction the droplet was traveling away from the source of the blood. The pattern forms a distinct curved line or often spaced evenly and becoming smaller outward. Many are elongated with tails and some vertical straight are present. Follows an arc typically of a swinging object. Droplets are medium-sized, often tear-shaped with tails pointing right, indicating movement direction. The difference between arterial and cast-off pattern, while in the arterial, blood pump from the artery under pressure rhythmically, while in the cast-off pattern, blood plung from a weapon or object as it moves through the air. First, contact prints allows investigators to gather several critical pieces of evidence. First, if the blood transfer is clear enough, it can provide rich data for the fingerprint or palm print identification, directly linking a specific individual to the scene. Additionally, the palm orientation of the print can determine hand dominance, either left or right, and provide a general estimate of the suspect hand size, which can help narrow down the physical characteristic. Finally, the placement and saturation of the print can reconstruct the suspect's actions, such as whether they were bracing themselves against a surface or where they move after coming into a contact print with a blood source. In determining the direction in a swipe pattern to which way the hand was moving, the head starts the sides of the pattern with the highest concentration of blood, and the most defined edges is typically where the motion began, and the lower portion of the palm area is much darker and more saturated, suggesting the hand initially made contact there, and feathering as the moves across the surface. The blood supply on the skin is depleted. This causes the edges to become streaky, lighter, and less distinct, as the tops of the fingers show feathered edges and vertical striation that taper off, indicating that the hand was moving in upward direction relative to the paper. The difference between these two patterns, you must look at whether the blood was already on the surface or on the moving object. A wipe occurs when an object moves through a pre-existing wet blood stain on a surface, effectively cleaning or smearing the original drop, while a swipe happens when a blood-covered object like a hand transfers blood onto a previously clean surface. You can distinguish them by looking for the skeletonized edges of a wipe, which show where the original stained perimeter had begun to dry before being disturbed. Blood behaves differently on paper because the porous fibers cause wicking, where the blood is pulled into the material, often blurring the edges and distorting the original shape of the pattern. In contrast, a non-porous surface like a tabletop doesn't absorb the liquid, allowing the blood to sit on top and maintain much sharper, more accurate details of the transfer. In the smooth surface or non-porous, the blood drop maintains its surface tension upon impact, resulting a circular stain with very clean, smooth edges because there is little resistance from the surface. The raw surface or porous, the irregular texture of the surface disrupts the surface tension of the blood, causing the edges of the stain to appear scalloped or spiked. This friction results in a smaller overall diameter compared to smooth surface, often accompanied by small satellite spatters breaking away from the main drop. Absorbing surface, the blood is quickly pulled into the cloths of the material, which causes the stain to spread internally rather than staying on the surface. This creates a fuzzy, diffuse edges where the spines follow the weave of the fabric, making an accurate diameter measurement difficult to determine. At the height of 1 foot, the drops typically produce circular stains with relative smooth edges because the impact velocity is low. As height increases, the diameter of the stains grows because the drop has more kinetic energy spread outward upon hitting the surface. At this specific lower height, you likely notice a lack of satellite spatters as the force of impact wasn't yet strong enough to overcome the blood surface tensions and cause it to rupture. As the height increases to 2 feet, you will notice a transition in the physical characteristic of the blood stain compared to the 1 foot marks. At 2 feet, the drops hit in the surface with noticeably more kinetic energy. You will likely observe that the diameter of the parent drops is slightly larger than those at 1 foot, may around at 1.1 cm to 1.2 cm based in our levels. As the increased velocity forces the liquid to spread further outward upon the impact, the edges characteristic of the stain at 2 feet begin to lose the perfect smoothness. Seen at lower heights, you might notice that the start of scalloping where the circular border looks slightly jagged because the energy of the impact is beginning to overcome the blood surface tension. While significant satellite spatters usually become more prominent at 3 feet and above, you may see the very first tiny spines or droplets breaking away at this height. In the 3 feet height, the shape is perfectly circular. The size of the diameter increases again, becoming larger than the 2 foot drops. The characteristic of edges starting to show slightly irregularities or scalloping. There is one satellite up in upper portion and second drop because they affected by the air resistance during the drop of blood from the surface. The forensic interpretation: at 3 feet, the force is sufficient to make the blood spread outwards, again increasing the diameter. The stain is now larger and flatter. This is the point where we start to see the physical effects of increased gravity and velocity. When the height increased into 4 feet, the shape of blood in the surface circular but significantly wider. The size, its largest stains in this series. The edges characteristic is irregular, jagged, or scallop. You can see the satellite stain are clearly visible around the parent drop. These are small separate spots of blood that broke off from the main impact. As a forensic specialist, I have examined these bloodstain patterns created at controlled angles of 90 degree, 60 degree, 45 degree, and 30 degree. The purpose of this analysis is to demonstrate the direct relationship between the angle of impact and the resulting shape, dimensions, and appearance of the stain. We use the fundamental principle as the angle of impact decreases from 90 degree to 0 degree. The stain changes from a perfect circle into a elongated ellipse. The 90 degree angle perpendicular impact. The shape, the stain is a perfect circle. Dimensions: width is 1.5 cm, length is 1.5 cm. The ratio is 1.5 equals 1. The characteristic: the edges are relatively smooth and symmetrical. There is no distortion, elongation, or directional tail. The forensic analysis or interpretation: when a blood strikes a surface of exact 90 degree, the force is distributed equally in all directions upon impact. This results in equal width and length. A ratio of 1 confirms that a perpendicular drop. This tells us the blood source was directly above or directly in front of the surface at the moment of deposition. The 60-degree angle. The stain is slightly oval or elliptical. The dimension: width equals to 1.2 cm, length is 1.4 cm. The ratio is 0.857. Calculated angle: approximately 59 degree, very close to the intended 60 degree. Characteristic: it is still quite round, but the length is now slightly greater than the width. The edges remain smooth, mostly intact, though minor spatter may be visible. Forensic interpretation: at 60 degree, the blood is no longer falling straight down. It is traveling at an incline. The impact force is no longer equal. It pushes slightly more in the direction of travel, causing minor elongation. The ratio is still high, indicating a steep angle. The 45-degree angle. The shape: clearly defined ellipse. Dimension: width equals to 1.4 cm, length is 1.9 cm. The ratio is 0.737. Calculated angle: approximately 47 degree, consistent with the 45-degree target. The characteristic: the difference between width and length is very noticeable. The stain is stretched out and the edges may show more irregularity or scalloping. The forensic interpretations: at 45 degree, the effect of the angle is very pronounced. The blood is moving horizontally as well as vertically. The stain compresses in width and extend in length. This is a common angle seen in many crime scenes involving splash or projected blood. The 30-degree angle. The shape is highly elongated and narrow. The dimension: the width is 1.1 cm, while the length is 2.3 cm. The ratio is 0.478. The calculated angle: approximately 29 degree, accurate to the intended degree, 30 degree. Characteristic: the stain is significantly longer than it is wide. It appears thin and stretched, often at swallow angles like this. You may see a distinct tail or satellite spatter indicating the direction of travel. The forensic interpretation: at 30 degree, the blood is skimming across the surface at a low trajectory because the angle is shallow. Most of the force is directed forward, causing the blood to smear and stretch out. A low ratio like 0.478 confirms a very low angle of impact. This is crucial for determining if the blood originated from a low position or from a distance. The use to calculate the angle is we use as arc sine divide width into length. I have completed with my team the reconstruction process using the stringing method to determine the origin of the bloodshed. My analysis follows the standard procedures in bloodstain pattern analysis. I will explain the step, the findings, and answer the critical question regarding this evidence. It's the finding area of convergence or 2D. First, we establish the horizontal location. I draw imaginary lines through the long axis of each bloodstain pointing opposite the direction of the tail. As you can see the photos, all these lines intersect at a common point on the surface. This is the area of convergence. It is a two-dimensional point that tells us exactly where on the floor or ground that event took place. Finding the angle of impact. Next is to determine the height, we need the angle. I measured the width and the length of each stain. And calculating using the formula angle, arc, sine, width, divide length, I determined the trajectory for each drop. This tells us how steeply the blood was falling. Then step 3, the finding the area of region of origin, the 3D. Finally, we move into 3D space. Using the calculated angles, I attached stringing to each stain and lifted them into the air using a protractor. The result, the strings converge in mid-air. In definition, the point where they meet is the area of origin. However, because perfect measurements are difficult, they form a small cluster or zone. This zone is called the region of origin. Axis of origin, if we draw a straight vertical line from the area of convergence up through this cluster, that is the axis of origin, representing the height dimensions. It indicates that the injury occurred from one distinct location, meaning the victim or the source was stationary when the blood was projected. A calculated height of 4.3 feet is significant. This height is correspondingly to the chest and shoulder level of an average size of adult human. This strongly suggests that the victim was standing upright when the injury occurred. Area of convergence. The area of convergence is the foundation of the entire reconstructions. It narrows down the crime scene to a specific spot on the ground. It serves as the anchor point from which we calculate everything else without knowing where it happened on the floor. We cannot calculate how high it happened. What the axis of origin? The axis of origin provides the vertical dimension or depth. It acts as our visual guide for the z-axis. It allows us to visualize the vertical trajectory and understand the line of attack. It connects the ground to the source in the air. The region of origin. The region of origin is scientifically important because it acknowledges the forensic science deals with real-world evidence, not perfect mathematics. It accounts for measurements, errors, and physical variations. It gives us a realistic sphere or zone where the blood source was most likely located, making our conclusion accurate and defensible in court.